Okay, so now we're going to look at using the second derivative and the first derivative to talk about graph sketching and asymptotes. Okay, so we have two objectives here. The first one is to accurately graph a function using knowledge of the first and second derivatives, and the second is to evaluate horizontal asymptotes of the function. Now, for the first one, we're actually going to do this mostly in class, but I want to at least give you a sense of how we're going to use this. We're going to use tools like the first derivative test, okay, the second derivative test, and these will identify maximums and minimums of a function, okay? Okay. The next thing we're going to do is we're going to use these also, the first derivative and the second derivative, to identify shapes. Okay. So we can get a sense now of what's happening in a given interval with the shape of the graph, with the maximums and minimums, and then we'll also use knowledge of x-intercepts or roots, okay, and y-intercept, okay, of f. Okay, so those things are going to help us graph functions without having to use a graphing calculator, which is pretty useful. Okay, they give you a quick indication of what the graph really looks like. All right, so we're going to do this mostly in class. It's applying things we've already done, so I'm not going to lecture on it right now. Instead, I want to look at the next objective, which is evaluating horizontal asymptotes of a function. And this is finishing up everything we learned about limits early on. And now we're going to look at limits at infinity and at negative infinity. Okay, so let's take a look at this function here. Now, the one thing about limits at infinity and negative infinity is 90% of the time, the limits are going to be the same value. Now, that's not always the case, but it's going to help us get a sense. So if we go to positive infinity or negative infinity, this function will probably go, partly because we've already indicated here by the notation, this is going to go to the same value whether I go positive or negative. Okay, so here's the basic way we're gonna do this when we have a polynomial divided by a polynomial, when we have a rational function. Here's the method, and you may have seen this before. We're going to divide both the numerator and the denominator by the reciprocal of the highest power of x in the numerator or the highest power of x in the denominator. Okay, so we look at this first of all. We say, well, what's the highest power of x? Highest power of x is x to the fifth. Okay, right there. So what we do here is we're going to divide both the numerator and the denominator individually by x to the fifth. Here's what it looks like. Okay, or another way to look at it is multiply the numerator and the denominator by x to the negative fifth. Okay, so same thing. Okay, what that does, this is the number 1. Okay. And it's legal to do this because the limit is going to positive and negative infinity, which means that these numbers are it's never 0 divided by 0, so this is a legal maneuver. And let's simplify a little bit. If I distribute this through, okay, I'm going to get 20 over x to the third, or 20x to the negative third, minus 3 over x to the fourth, which is the same as 3 times x to the negative fourth. Oh, that's actually a little typo. There should be x to the negative fourth. Divided by 3 in the denominator, minus, because 3 over 3x to the fifth over x to the fifth, minus 4x to the third, negative 3, pardon me, and plus 5x to the negative fifth. Now let's see what's going to happen here. Let's do a little bit of review here and ask, what happens to the function 1 over x as x goes to infinity? Okay. Now, you can think about this for a second. As x gets continually larger, what's happening to the reciprocal of that? Okay, it goes to 0. Okay. Now, what about 1 over x to a power? Something bigger than 1, so x squared. This is also going to go to 0, but even faster. Okay, so that's an important concept, right? It goes to 0 and it goes to 0 faster. So what's that mean? 20, let's just look at this one little bit right here. This is 20 over x to the negative third. If I let that approach infinity or negative infinity, where is this going? Well, 1 over x to the third has to go to 0 because it's just going to 0 faster than 1 over x to the second. So this goes to 0. Okay, 20 divided by x to the third goes to 0 as x goes to infinity. How about this? 3 over x to the fourth. that goes to 0. Well, 3 is just a number. We don't have to worry about that. That doesn't go anywhere because there's no x. This must go to 0, and this must go to 0. Okay, so at the end of the day, what are we left with? We're left with 0 over 3, which is 0. So one way to evaluate these, and probably the best and most effective way, is to divide the numerator and the denominator by the highest power of x. Okay. All right. There's one other way we can look at this too. So whenever we're evaluating x going to infinity or x going to negative infinity for a rational function, basically the concept is this. The limit will go to 0 if g of x gets larger faster than f of x, and will go to infinity if f of x gets larger faster than g of x. Okay? If the numerator is climbing at a higher rate than the denominator, okay, it's going to go to infinity, and if the numerator is climbing at a lower rate than g of x, then the denominator is going to go to 0. Now, here's the thing, right? Rates are a little bit relative at this point. Okay? We look at, in our way of thinking, 3x, and x, even though 3x is bigger than x, these go to infinity at the same rate. Okay? So, in this particular case, we would look at this as not going to 0 and not going to infinity. This is going to go to a number if I have the ratio of 3 of x over x. Okay? However, x and x squared go at different rates. Okay? We think of quadratics having a different rate of change, okay, fundamentally, than a linear function. Okay. So here's the theorem we're gonna be able to use to get by. Now, this theorem is a nice theorem and it's a quick way to do things. However, the previous method will always work, even when this breaks down a little bit. So we're talking about a rational function divided by a rational function. This will always go to the ratio of the leading terms times the limit as x goes to infinity or negative infinity of the difference of the highest powers. Let's see how it works in relation to the previous. Here was our previous problem. Oh, and we should not have, we're not using this method now. Okay, that's not there. Using this theorem here, we say that it goes to the quotient of an over bm, that's 20 over 3, times the limit as x goes to infinity of n minus m, which in this case is 2 minus 5. Another typo, pardon me. 2 minus 5. Now 2 minus 5 is negative 3. So this is 20 times the limit as x goes to infinity or negative infinity of 1 over x to the third. This goes to 0, which means that I get 20 times 0, which is 0, which is the same as the previous one that I got. Now one thing I want you to notice about this that's interesting is if n and m are the same power, where does this go? So if my top function is something like 3x to the 6th, do it like this, plus 5x squared minus 2, and my bottom, my denominator is 5x to the 6th minus x to the 4th, where does this one go? If this is my numerator and this is my denominator. Well, it's actually, it's kind of interesting. This one, since n and m are the same number, when I take the limit as x the limit of x as x goes to, the limit of x to the 6 minus 6 is x to the 0. Well, that's just 1. So if I take the fraction of the quotient of this function divided by this function, the limit as x goes to infinity will be 3/5. Okay. What we're saying is that any polynomial of degree 6 climbs basically at the same rate once we get really, really large numbers as any other polynomial of degree 6. Okay. So that's what's kind of interesting about it. The degree of the polynomial matters more than the lower terms. These lower terms after a certain point are insignificant. Insignificant after a certain point. Okay. What really counts is how fast is the highest power climbing. Okay, that's what really counts. All right. Thank you, everybody. I'll see you in class.